Dr. Wagner, for the opportunity to present this here for you. And my idea here is to show this ongoing working. We have some interesting results, and we are focused on solving hyperbolic PDEs, okay, using physics-informed neural networks. So first, now why? In petroleum engineering, more specifically in reservoir engineering, we use a lot numerical reservoir simulation, where we have numerical methods that would like to predict oil production, water production, and all the interactions that happens in the subsurface. And as you can imagine, these are very complex models. These are 3D models, multi-phase, and sometimes reaching billion of grid blocks. And these simulations can run in several hours or a few days, running very big computers and very expensive computers as well. And the companies are actually increasing the complexity of models. So, for example, here this is an image of a benchmark model. This is a very small model, but all these properties, these are subsurface properties. They are, for example, here this is the porosity, as you can see in this color map here. And the porosity of the rocks that are on the subsurface, and here you have several wells. And our model simulates the numerical reservoir simulator simulates the production when you open a well and you have some oil and you have pressures and saturations changing. And this is a very complicated model, and we also have a lot of uncertainty here. Okay, so this is underground, and geologists have an idea what is going on, but we have a lot of uncertainty. And to deal with this uncertainty on our predictions and our estimation is very expensive as well. So sometimes we have to run thousands of models to get uncertainty quantification, for example. So this is very expensive, and building a proxy and a fast proxy model for this reservoir simulation is a challenge that many have tried, and we have some good proxies that work well in some specific areas, but our idea is, can we build this a proxy model for the reservoir simulation based on pins? Okay, so as I told you, this is a kind of a very complicated model. Let's first try in a simpler related problem. Okay, and the problem that we are going to deal here is called the Buckley-Levitt problem. This problem comes up for the fact that we have to inject, in most of the case, we have to inject water in the reservoir in order to be able to extract more oil. So we inject all water for two reasons, mainly to keep the pressure of the reservoir. Okay, we are removing oil, so the pressures go down. We inject water to keep this pressure up, and also to have this effect of sweeping. We are sweeping the reservoir, injecting water, and the oil goes out. And this Buckley-Levitt problem is a classical problem on the engineering, petroleum engineering. And as you can see, is a immiscible 1D displacement. It's just 1D. It's very simple, and it's a nonlinear hyperbolic transport equation. Okay, so we are modeling water saturation. Okay, that's our main variable, and we have some initial conditions and boundary conditions. And what we are modeling here is like we have a reservoir, a domain saturated with oil, okay, with water saturation 0, and we start injecting water in the boundary 0, and we keep producing oil on the x equals 1, and so this water moves to the right, like sweeping the reservoir. Because of the complexity of the interactions between the oil and the rock itself, the grains of the rock, you may have a lot of forces acting here. And this is a very complicated field where people study this interaction between oil, water, gas on the microstructure of the reservoir. And this study here can generate a flux curve, okay, that this depends on these interactions of the grain and the fluids inside of the reservoir. And this will dictate how our flux will happen. Okay, so this flux, for example, I'm going to show here on the left plot here. This is how this process happens during the time. We have an analytical solution for this. It uses method of the characteristics to solve. And let's see, how can I play this? Oops, it's not working as I was expecting. I'm sorry. So as the times go on, and I'm injecting here on x equals 0, my water saturation keeps increasing. And you can see here in the top plot, in the middle plot here, also you can see there is a spreading, okay, or a rarefaction when you go to the hyperbolic PDEs, a refraction, and there is a sharp shock here, okay, where the saturation changes from maybe 0.6 to 0. Okay, so this is kind of tricky to to obtain this using, for example, numerical methods or something related to that. Depends on the discretization and a lot of stuff. But there are a lot of methods that can deal this with no problem. Okay, so this is the idea. This is the problem that I'm trying to solve with pins. Okay, I'm sorry. So in last year, Fuchs and Chalapi at Stanford University, what they did to solve pins, they add a diffusion term, as you can see here on the right side of the equation, with an artificial viscosity. I'm calling the artificial viscosity here epsilon. And by doing this, it was possible to solve this problem. Okay, so this addition of the artificial viscosity is kind of a known method that we can solve. You can use to solve this type of hyperbolic PDEs. However, it needs to choose the value of the viscosity. Okay, and as you can see here, here is my blue. The blue is my solution, my exact solution, solved by analytical methods, and the orange one is my solution based by using pins and this artificial viscosity here with a chosen fixed viscosity value. So to solve this hyperbolic PDE, in fact, this is not hyperbolic anymore. If you add this term, we we need first to define the artificial viscosity coefficient a priori and apply this artificial viscosity coefficient in the whole solution domain. So we are not only, we are applying this artificial viscosity in the whole domain in points that we do not need it. Okay, so for example, here in the rarefaction, we do not need this. These artificial viscosity terms will need to be applied only on this shock front. And in case you choose wrong the artificial viscosity, you can see that the methods fail completely. If you choose a large value, you have a smoother shock front. That's this red curve here. If you choose a smaller value, that is the green line, you see that the methods fail completely to capture the the shock front in all the solutions. So this turns out to be the idea of our solution. Can we apply can we apply the artificial viscosity only where it is necessary, for example, close to the shocks, and instead of defining the artificial viscosity a priori, can we learn their values and location during the training process. And we say, oh, yes, we developed this method called PIN ALAV. It's an acronym for PIN with adaptive localized artificial viscosity. Okay, so the main idea is, okay, this is our PDE for the Berkeley Levitt. We now, instead of having an epsilon that is a fixed value, this is now a learnable variable, and it's function of x and t. And when we define the loss function, this first three terms are the main standard pins, and we add here a term that is called viscosity or artificial viscosity loss. That will be just the L1 norm of the viscosity field, artificial viscosity field. So just to do a quick comparison between pins, here is like the standard way of the pin defined to solve this hyperbolic PDE, where we have the PDE conditions, we transform the PDE on the residual form, and we train these neural networks, we train A neural networks to minimize these three, the summation of these three loss functions, and we have this total loss function here. What we are proposing is, okay, we now have, again, a learnable, localized artificial viscosity, is this time epsilon. We are going to learn this also during the training process, and we define we have the residual equation again, but it's with this term here, and we have our loss function, and we also have the total loss function that now is not function only on the weights of our neural networks, but it's always function of our artificial viscosity field. And as you can see, we can get very good results with our PIN ALAV. Here is this orange curve. Okay, when we compare this with the PIN traditional with a fixed artificial viscosity. We are still working on this to make the error better and to have more consistent result. But the more interesting thing is if you take a look on the map of our artificial viscosity, you can see I have here X on this axis here on the bottom. You have time here, and so you can see that the values that are not zero for the artificial viscosity are going on this line here, okay, across the domain. And this coincides with the shock front. Okay, so where the shock front is, we have different values of artificial viscosity. So we are capturing the front evolution only on the artificial viscosity. So we are applying the artificial viscosity only we need it. Okay, so this was the idea of the PIN ALAV. And here as another example using Burger's equation that is more familiar to some. And with a sinusoidal initial condition, you can see that we can solve using pins with a fixed artificial viscosity. This is not artificial, but it calls viscous Burger's equation. But if I reduce this viscosity here from 0.01 over pi to 0.001 over pi, you see the pins fail. That's the green line. Okay. However, if I use the PIN ALAV in order to solve the unviscid Burgers, okay, you can see a very good match, and our error is better than applying to the fixed one. And you can see here, this map is in the same way. You have axis and time here, x and time, and you can see there is a very tiny line across here on x equals 0. That is exactly where the shock front happens. And this on time 0, that is this bottom part here, on time 0, there is no need for artificial viscosity because there is no shock front. Okay, so these values start to increase only when we see the shock front happening. And just to make a better plot, I have this 3D plot here on the top bottom right, where you can see the values of the artificial viscosity spiking only on the area where the shock is happening. Okay, so this was the idea, and it was a short presentation, but what we are getting, PNA Lab is a new method to solve these hyperbolic PDEs. We are localizing a learnable artificial viscosity to allow pins to solve these hyperbolic PDEs with shocks and or discontinuities. We also noticed that self-adaptive pins proposed by McLean and Dr. Braga Neto on the initial condition improves our response. And if you like acronym like me, this will be SAP in a lab, okay, this method. And we are trying to looking for better performance of this method, trying to a more consistent method. Sometimes we do the same training and we got different results. We are working on this and trying to improve the training. And hopefully we are going to be able to apply this to the Buckley leverage problem that will be much more complicated, and we do not have too many solutions for the 2D Buckley leverage problem on the literature. So that was what I had to present, and thanks again for the opportunity.
Thank you, Emílio. That was a really good presentation, and very promising line of work here. I'm already familiar with this work, of course, but are there any questions from the audience?
Hi, Emílio. This is how very nice work. So I have some question about like the regularization term. You already tried the L1 norm, right? For the artificial viscosity. Have you tried the L2 norm?
Yes, in fact, I have tried this, and the L1, it seems to be working better.
Okay.
Our idea to have this L1 is in fact to have more values zero. Okay, yes. Only exactly what you need. You have non-zero. So I guess this L1 it's helping on this way.
I see.
But the difference is not very big. It's subtle when you use L2.
I see. So like how did you determine your alpha parameter? Just try and error?
Yes, currently I'm using try and error.
Okay.
Yeah. But after your presentation, I am trying to maybe put just softmax and some learnable stuff there.
Yeah, sounds great. Thank you. Yeah.
Thank you.
I should say that Emílio is already a veteran in applying deep learning to petroleum engineering problems. He has other work using deep neural networks, deep autoencoders, and so it was a natural step for him to start applying pins, and so we are very happy, fortunate to have Emílio. And any other questions?
Hello.
Luis.
Oh, sorry.
Yes.
Emílio, nice work. I would like to know about the data you use to test the models. What is the region, or what is the sample data you use?
In fact, for my approach here, I'm not using sample data. This is only based on the PDEs itself. As you can see here, my loss function. Let's take a look on this left loss function. I only have the residual loss function and the boundary condition loss function and the initial condition. So there is no data to train these pins. We are only based on the PDEs and the conditions itself.
Okay. Thank you.
That's a nice question, because if I had data, I could add data to this process. But at this point, I'm not adding yet. Okay, and I'm trying to solve this. I'm trying to apply the pin only as like a PDE solver.
But this could be a future step, right?
Yes. In fact, the original the most famous Beans paper, he added a data term here that you can use the data to improve your model.
Oh, perfect. Thank you.
So, for instance, suppose you don't know the concentration on the injection site. Then you could use some data to, so you can trade off boundary conditions, initial conditions for data. I mean, that's one of the things that neural networks allow you to do. It's not simply a PDE solver, even though we have to start with that. I mean, we have to look at you know, if you can solve the forward problem, but the inverse problem is also very promising. So I think there's a lot of potential for reservoir simulation. You know, I mean, we're still not there. I mean, it's still in the future, but you know, there's potential for this to become something practical down the line.
Yes.
For oil
yeah, if we can step it in, I just want to follow up on what you said. There was a natural choice of Emílio doing this work, but actually it is a step back from what we were actually doing, right? So Emílio had another paper on doing, you know, as Ulysses mentioned, autoencoders, a mix of model reduction and autoencoders and so forth. But in fact, you know, it's not what we found out is not very generalizable in some ways, right? Sometimes it fails, right? So the idea then was, well, let's start with a very simplistic reservoir simulator that we can have, which is the Buckley-Leverett, right? Which is a very simple. We have analytical solutions, we have everything, so that we can at least try to understand where these failures are coming from.
Right. Absolutely.
And then once we do that, now we can you know, precisely move up to a more practical sense and say, well, now we have a big reservoir, we have a 2D, 3D, multi-phase. How do we do that?
Oh yes, I see. Very, very good point. Yeah, that's definitely a good point. I mean, we want to make this more realistic and more complex.
I mean, if you cannot guarantee for a you know, the Buckley-Leverett, if you can guarantee a solution, a reasonable solution, then things may not work for a more practical problem.
Right. But this is a very nice model. I mean, like a benchmark. Yes, like I said, it has some very interesting phenomena. You know, the shock. You know, you can of course set the parameters to follow the geophysical properties of the reservoir. You can explore all of this. I mean, you can in fact do inverse mapping of the parameters of the rock.
Absolutely, absolutely.
And I mean, do they actually do this? Like, do they this kind of experiments where they inject water in order to discover let's say the porosity?
Oh yeah, this is a common process called history matching in petroleum engineering.
I see.
Which is basically you know, system identification in some ways for
exactly.
And in our cases, sometimes this is a problem because we have a bunch of data and we'd like to match our reservoir simulation, but the reservoir simulation takes a lot to run. So if we would like to apply gradient-based methods, we have to run the simulator and calculate derivatives and run again, and this takes a lot to do history matching without traditional models. And if we have something faster and clever like Beans, maybe we can history match in a very
and of course a very natural extension to this, if you go and make the Buckley-Leverett a stochastic process, right? In some ways, with the parameter inside, right?
Stochastic PDE.
PDE, exactly.
Yeah.